Hiya, today's video is on stationary waves. So let's just get started. So this is also the result of superposition. So if you have two waves, so one wave going in right direction, and suppose it hits a boundary, a rigid boundary, and gets reflected back. So when it reflects back, it comes back in a phase difference of pi with the original wave. So it's kind of inverted with respect to the incident wave. So I'm just taking another color here. So the wave that will be reflected back from the rigid boundary here would have kind of this proposition here. So it's inverted with respect to the incidence. So the purple one is the reflected wave. So if your incident is going, then the reflected would be coming back like this. So the resultant of these two waves is producing a pattern, which pattern is called stationary waves. So the condition is the two interfering waves or superposition of two waves which are moving in opposite direction. Two waves in opposite direction. So that's one condition, and they should have same frequency. And they should also be coherent. So coherent, as we saw in the video of interference, is the waves which have same frequency and constant phase difference. So if the waves are coherent and they are traveling in opposite direction, they produce stationary waves. And if they are coherent and they travel in same direction, they produce interference pattern, constructive and destructive. Now, what exactly happens in a stationary wave is, just trying to make a diagram here. So if you have, let's say there's a string, and on this string you have this wave which is reflected from the rigid end. So from this end it is reflected. So the reflected wave is opposite in a sense of pi. The phase difference between the purple and the red wave is pi. So they are producing. So this is a look of a stationary wave. So at this position is called node, which is stationary. The nodes on stationary wave have zero amplitude. They do not move. They behave like fixed position. And this position here, which has maximum amplitude, is called antinodes. So this is antinodes. So antinodes are the position of maximum amplitude and nodes are the position of minimum amplitude. And the distance between, so as you can see, the distance between consecutive nodes is half the wavelength. So obviously between adjacent node and antinode, it is lambda over 4. Now, what is node? Node is the position of minimum displacement, minimum amplitude or minimum displacement. Now, these positions are fixed, so they do not change. So if position A, B, and C have zero amplitude, they will forever have zero amplitude on a stationary wave. If the position D has maximum amplitude, or both the position D's would have maximum amplitude, they would not change. Unlike a traveling wave, if it's a traveling wave, the amplitude of every position is same. Ultimately, every particle would reach the maximum amplitude. But in stationary wave, every position has a different amplitude. It's fixed. The amplitude is not changing. Say this one reaches only up to here. The particle at D reaches to the maximum height. The particle at B is zero amplitude. So different positions on a stationary wave will have different amplitudes, whereas different position on a traveling wave will have same amplitude. Okay, so just to remember, then if I have, let's say, just trying to make a diagram here, if I have a string set up on a pulley kind of arrangement with weight hanging on it. So what if I set up stationary waves on this, I can make this string vibrate in stationary wave pattern. So if that happens, so this is how. Now, so as you can see, these positions are the position of nodes then, and these are the position of antinodes. Now, to understand the waves on the stationary waves on string, we first need to see what is the wave velocity on string. So the wave velocity on string depends on, so if you have a string, let's say, hanging from a ceiling and there is a weight hanging on it, okay, so the weight is, let's say, m, so the tension in the string is mg. Now if this tension is increased and there is a wave on this string, let's say the wave on this string is something like this, okay, and if I increase the tension, it is found that this wave travels faster. So velocity is, this is given in your equation sheet, so T over mu. So mu here is linear mass density, and is equals to mass of the string divided by the length of the string, and is measured in kg per meter. So as you can see, the velocity of a wave on a string is square root of tension over mu. So larger the tension, so if I increase the weight of this mass here, the wave velocity would increase because the tension has increased. So larger the tension, larger is the velocity. Now, how the stationary waves are produced on string, before that, let's try and do some question pause before you hear the answer that I have to say. The condition that is essential for the formation of stationary wave is that it should have two waves of equal frequency traveling in opposite direction. Which statement about particles in stationary waves is correct? What is correct? Does all the particles move with the same amplitude? No. Particles at nodes and antinodes are always in phase. Okay, that one I have to tell you. Let's just see. The answer is this one. Let's just go back. So all these particles in this loop here, they are all in same phase. So they all go to the maxima at the same time. Okay, and these ones would go down. So if you see, adjacent loops will be having a phase difference of pi, but the particles in the same loop or between adjacent nodes they are all in same phase. So the particle between two adjacent nodes are in same phase because they all become maximum at the same time and minimum at the same time. Which is correct again? Two adjacent nodes is equal to one wavelength. That's not right. That's lambda over 2. So if you see a stationary wave is of this form. So adjacent nodes is lambda over 2. So this is wrong. Node and nearest antinode is one wavelength. So node and nearest antinodes is wrong again. It is 1/4. Between two adjacent node is half a wavelength. So that's answer is right. Two adjacent antinode is again half a wavelength. Okay. Now the stationary waves on strings. For the stationary waves on string, the first thing that you need to know is the wave velocity that we have just done. So what we have in our A-level syllabus is that we need to know what is the minimum possible frequency a string can vibrate in, and what's the maximum possible frequency. So we're doing the first case when a string is vibrating in first harmonic. So first harmonic is minimum frequency. So the minimum possible frequency a string can have is the first harmonic. Now if I make it, so let's say there's a string which is tied up between two fixed ends, and the string has length L. So if I want minimum frequency for this string, it would have the fixed end is always a node, so this would be a node. So a wave will go here and will come back. So this is a minimum frequency. So this is how a string in first harmonic look like, just one loop. Now what is the distance between two adjacent nodes? That's lambda over 2. So your length is half the wavelength. So rearranging 2L is lambda. So if I calculate using my V equals to F lambda, try and calculate frequency. So V over 2L is the formula for fundamental frequency. So first harmonic or fundamental frequency. Now second, so if I want, after first harmonic, the second harmonic, if I want my string to vibrate, same string to vibrate in the second harmonic, tied between two ends. So the length is still the same, but because I want the second harmonic, it will now have two loops. Okay, they will be equal sized, say 2 loops. So this is then, again, the fixed end is always a node. So remember that. So if I just do again the same thing, the distance between two adjacent nodes, this is lambda over 2, and this one is also lambda over 2. So my length would be then lambda over 2 plus lambda over 2, that is lambda. So if I use the same formula again, V equals to F lambda. So the frequency in this case would be V over lambda, and lambda is here L. So the frequency is double this frequency. Here the frequency was V over 2L, now the frequency is V over L. It's double the first harmonic, so it will be called as second harmonic. Similarly, you can try and go ahead and try the third harmonic. I'm doing it per posit. You try to make the third harmonic. So the third harmonic would be again the same length of the string. The length is not changing, but the number of loops are increasing because you're increasing the frequency. So it's like somebody's playing on a guitar string and he's plucking at 3 different positions. So if the plucking is happening here and here, so then this would act as nodes. So now the length of the string is not changing, but the guitar is making more sharp, high-pitched sound because the number of harmonics have increased. So now my length will be 3 times half the wavelengths because 3 lambda over 2 are there. So if I rearrange this, 2L over 3 is lambda. So using V equals to F lambda, my frequency would be then V over lambda. And then plugging in the lambda, I get 3V over 2L. So that's the frequency. So 3 times the fundamental frequency. That is why this is called third harmonic. So similarly, a string can vibrate in any harmonic. And let's say if it vibrates in fourth harmonic. So the fourth harmonic would be 4V over 2L. So the fundamental or the first harmonic is V over 2L. So if you just times it by 4, it'll be fourth harmonic. Fifth harmonic, 5V over 2L. Sixth harmonic, 6V over 2L, and so on. So these are called harmonics on a string. So on a string can have different harmonics depending on what frequency it is vibrating in. But the minimum frequency any string of length L is always V over 2L. Okay, let's do this question. A stationary wave is formed on a stretched string. That means it has tension. Which is correct? Tension on the string varies along its length. No, the tension is same everywhere. The speed of the wave is 0 at nodes. The speed of the wave is 0 at nodes. That is right or wrong. For that, you have to just think that a wave, if it becomes 0, then it is not moving. And if it is not moving, it cannot produce a stationary wave in combination with the first wave. So that is not right. The distance between adjacent antinodes is half the wavelength. So that is right. It is always half the wavelength. A stretched string of length. Okay, you go ahead and pause and try it. I'm going to draw the diagram here to make you understand it more. Length is 0.8, fixed at both ends, vibrate in second harmonic. So now what I have is 2 loops here. Okay, this is my second harmonic. Wave speed is 160 and it wants me to calculate the frequency. What I'm doing is I'm going to calculate wavelength. This is given as 0.8. So this is half wavelength plus another half wavelength. So lambda is 0.8. That gives, so my wavelength is coming as, writing lambda plus lambda over 2 is 0.8. So lambda is 0.8. So using then V equals to F lambda, 160 divided by 0.8, that would be my frequency. That would be 1600 divided by 8 is 200. So 200 hertz is the frequency of vibration. Yeah, that's the right answer. Okay. Now let's try this one again. Again, pause and try it yourself, or else just see how I'm doing it. A string of length 1.2 meters is fixed at both the ends. At least when you're trying to learn something new, at that time, every time draw the diagram. It'll just help your mind to make the mental models of whatever new thing you're learning. Okay, so fixed at both the ends. Always remember, a fixed end is always a node. It has a mass of 6 grams, length is 1.2 meters, tension is 96, third harmonic. Okay, so third harmonic means 3 loops. I should have 3 loops here. So every loop is lambda over 2. So the length of the string is 3 lambda over 2. So 2L over 3 is lambda. 2 times 1.2 divided by 3.4 times 2 is 0.8 meters. So the wavelength is 0.8. Now you want velocity. All right, so velocity is not given. So we need to calculate velocity using T over mu. Tension is given, 96. And we need to calculate mu, which is linear mass density. And mu is mass over length, linear mass density. So mass is 6 times 10 to the power minus 3. You have to convert this into kg. Yeah, you know that. Divide by 1.2. So that is 1 divided by 0.2 is 10 divided by 2, so 5. So 5 times 10 to the power minus 3 kg per meter. Plugging it here. And then solving, I get my velocity as 138.6. So I'm getting my velocity as 138.6 meters per second. So got the velocity. Now I need to calculate the frequency. I'm doing it at this end. So frequency is V over lambda. V is 138.6 and lambda is 0.8. And then using my calculator is around 173 hertz. So 173 hertz. Okay, this is me solving it for you, or else, oh, we have the answer here, so it is 173 hertz. Okay, let's try. Now you can also have stationary waves in air columns. Now imagine somebody playing guitar, he's producing stationary waves on strings. Somebody playing a flute is producing stationary waves in air columns. So what is in closed end tube? Okay, let's just start with an open end tube first. So if it's an open end tube, okay, something like a flute, say if somebody is blowing into the flute, what is happening is, because it's open end, the open end would always behave like an antinode. So you'll have an antinode here and you'll have an antinode here. So for the minimum frequency, that's the first harmonic, your open end tube, so a wave would something look like this. Okay, that's good. So this. So this is the first harmonic, because you cannot have any minimum, anything less than this in an open end tube. So if the length is L, so the distance between consecutive antinodes is lambda over 2. So my length is lambda over 2. Lambda is 2L. Again, V equals to F lambda. So F will be V over lambda, so V over 2L. So that's so similar to our string stretched at both ends. If I have to get the second harmonic, you go ahead and try it yourself. How would the second harmonic in an open end tube look like? So I'm going to, again, let's say the length is still L, so length is not changing, but it is higher frequency, it is higher pitch. So what would the loops look like? Something like this. Okay, yeah, something like this. So this is again L. By terms of wavelength, this distance is lambda over 4, antinode and node, node and node, lambda over 2, node and antinode, lambda over 4. Anytime you think like this is, sorry, I don't remember that, go back and redo the thing, but don't give up. Don't ever give up. Okay, keep trying. There's nothing difficult if you know it. It's just difficult because you don't know it. So if you add all of that, that comes out to be lambda. So I get my frequency as V over lambda. So that is V over L. So as you can see, this one is twice the fundamental harmonic or the first harmonic. So the second harmonic is 2 times the first harmonic. Similarly, the third harmonic would be 3 times the first harmonic. So it's exactly same as a string stretched in the 2 ends. Only thing is the loops look a little different. In a stretched string, the end is a fixed end, so it forms a node. In an open end tube, the ends are open, so they act like antinode. So if I have now in the closed end, so let's just write here harmonics in a closed end tube. So if it is closed at one end, closed end tube, how would it look like? So, a clarinet would act like a closed end tube, but how would the harmonics look like in a clarinet? Okay, let's just see. Something like this. It's closed at one end. Now guess what would be formed at the closed end when it's producing a stationary waves. So at the closed end, it is a node, and at the open end, it is an antinode. So if the length is L, the first harmonic here, the frequency of the first harmonic, so this L here would be lambda over 4. The distance between antinode and node is lambda over 4. Rearranging, my lambda is 4L. Say frequency is V over lambda, so V over 4L. So can you see? So tell me, whose sound would be higher pitched if you have same length open end and a same length closed end tube? Whose sound would be higher pitch? Clearly the open end, because that is V over 2L, this is V over 4L. So this is a little bit higher, lower pitch. But let's see what happens next. So the next harmonic, how would it look? Let's just see. So something like this. Okay, so lambda over 4 here, and this is lambda over 2. So the total length would then become 3 lambda over 4. So my lambda would be 4L over 3. So my frequency, which is V over lambda, would then become 3V over 4L. So see how many times it is the first harmonic. So this is the first harmonic. So this is 3 times the first harmonic. So this is the third harmonic. So second harmonic is absent. So if you do the next one, it'll be fifth harmonic. So fourth is absent. So even harmonics are absent. It has only odd harmonics. Okay, first, third, fifth. You can try the next one. So odd harmonics are present. Say the next one would something. I'm just making it horizontal. Do I have next slide free? Okay. Wait, let me just do one thing. Add one more slide to it. Yeah. All right, so let's just see one more. So if I have, this is what this PowerPoint does. The minute I press escape, it goes back to its original color. Its original color is red color. I don't know why is that. So if I do the next one would look something like this. Okay, so something like this. So what is it now? So this is length L again. So this is lambda over 4, lambda over 2, lambda over 2. So my L here is then 5 lambda over 4. So rearranging, lambda will be 4L over 5. So frequency is V over lambda. So this becomes 5V over 4L. So see, it is 5 times the fundamental or the first harmonic. So this is fifth harmonic. So that's your closed end tube. Now let's do some questions. An open pipe. So this one is an open pipe. Be careful in the questions whether it is an open pipe or a closed pipe question. Pause and try to do it yourself. It produces its first harmonics. So as I told you, I'll try and make diagram, and this is what you also should be doing. Draw the diagram for the first few questions, and once you are good at them, you can stop making the diagram. So this is L, and so this is 0.85, and also this would be lambda over 2. So lambda is 1.7 meters. and V is 340. So just divide V over lambda, you get the frequency. So that is, wait, what? This solution is wrong. It is not a closed pipe. See, so this is wrong. It is an open pipe. Okay, so you calculate frequency using 340 over 1.7, which is 17 twos are 200 hertz again. All right, let's do the next one. Yeah, that's the answer. So this is the right answer. Okay, our pipe closed at one end. So this time the pipe is closed at one end. Go ahead, pause it yourself and do it. Closed end. It produces third harmonic. Okay, so if it is third harmonic, okay, this is the third, because remember the second is absent here. So this is L. So my frequency here is 3V over 4L, third harmonic. V is 330 and L is 0.75. So check the answer. I'm going to just do using calculator. Give me a second. This is coming as 330 hertz. Okay. Now, stationary waves in resonance tube. Now, this resonance tube method is used to calculate the speed of sound in air. So what it does is, so it is just used to measure the speed of sound in air. So let's just see how it looks like. So it is, okay, it is a very simple setup. It is consists of a long cylindrical tube, at the bottom of which there is a rubber tubing. This one is a glass tube, which is cylinder, which is filled with water, and this tubing is connected to a water source. Okay, so there is more water here. What is the purpose is, the level of this water is moved up and down till the resonance is heard. Now resonance means, this word means, so whenever resonance happens, the amplitude becomes maximum. So if the amplitude is maximum, a very loud sound is heard. Okay, now what is done is, a tuning fork is a kind of, this kind of structure is just a piece of metal with a U and a stand. It just look exactly like this. So what is done is, you just bang this thing on a rubber padding. So you hit this on a rubber padding and it produces a sound wave, and then you bring this near the mouth of this resonance tube and you change the level of this water. You keep changing till a loud sound is heard. So that is the point of resonance. And then you again change the level of the water to hear the resonance again. So this is what happens. Now, if you see the physics of it, this is what's happening inside the resonance tubes. So at the first resonance, so if this is the water level, so when the first resonance is heard, the tuning fork, the sound from the tuning fork travels and hits the water surface, reflects back, producing an antinode at this surface and a node at this surface and antinode here. So you can read this length from the cylinder because it's a graduated cylinder, and then you change the level of the water again until the next resonance is heard, next loud sound is heard. Oops. Until the next loud sound is heard. Say, let's say you lower the water level and the next resonance is heard when it is the third harmonic. And then you read this length too. Okay. Now, clearly, because it's the same sound, same air, it is being produced in the same medium, so the velocity remains same and the frequency is also same. So now what you're doing is the frequency is changing, and because the wavelength is changing. Now what you do is, from this L1, now this L1, because this antinode will not be formed exactly at the end, it is formed a little higher. So okay, so it forms little here, little above, so you don't know this. This small purple part is called, I'm labeling as E, and this E is end correction. So L1 plus E will be lambda over 4. Okay, now you don't know lambda, you don't know E. So that's why you're doing the second resonance here. So I can write second resonance as L2 plus E, because that is also going to form a little above. And because the same experimental setup, so whatever error you have here, this is a systematic error. So whatever error is happening here is the same error happening here. So L2 plus E would be, so lambda over 4 plus lambda over 2 is 3 lambda over 4. And then when you subtract both of them, so you get L2 minus L1. When you take away this from this, you'll get 3 lambda over 4 minus lambda over 4 is lambda over 2. So this is how you can calculate the wavelength. So once you know the wavelength, you can calculate the sound velocity. So that's the resonance experiment. Okay. Now this is a setup which is used to calculate how the frequency of harmonics on a stationary wave depends on the tension. So we have done that the tension is, the velocity is root T over mu. Now if you increase the tension by adding more weight here, what would happen to the frequency? The frequency would increase. Frequency is directly proportional to square root of tension. So tension increases, frequency increases. Okay. Also, what else you can do to increase the frequency is by changing mu, by taking a thick string. So if I take a thick string which has more mass per unit length, so if mu increases, more mass per unit length, your frequency would decrease. So the frequency, now why the stationary wave would be produced? Let's say if a wave is produced from this end, okay, it is going to reflect from this end because this is a rigid end. Whenever a ray wave reflects from a rigid end, it produces a stationary wave. So with nodes and antinodes. Okay, let's do this question. A resonance tube is closed at one end. Tuning focal frequency 340 Hz produces the first resonance when the air column length is 25 centimeter. So the frequency is 340 Hz and the air column length is 25 centimeter. What is the wavelength of the sound? The node is at the open end. At the open end, you have antinode. So this is clearly wrong. Only odd harmonics are present in the tube. Yes, that is right. Because what kind of tube it is acting? It is acting like closed end, but the water is acting like the closed end. So this is right. So this is wrong. Clearly, we are using this method to calculate the speed of sound. A resonance tube is closed at one end. First resonance occurs at length 0.3 meters for a tuning fork of frequency 256. So So the tuning fork is, the frequency is 256 Hertz. Okay, now this is the tuning fork, the resonance tube. First resonance is this. So length is lambda over 4. 0.3 times 4 is lambda. So lambda is 1.2 meters. So V equals F lambda 256 times 1.2. So that is 307.2 meters per second. Open end, so both ends open, shows second resonance. Again, I am doing the diagram. You can try to do it yourself first. So second resonance, say something like this. So this is the length, or you can just write, if it is second resonance, F is 2 times V over 2L. So V we want, so this is 400 Hertz. Velocity over length is 0.85. So 400 times 0.85 is the velocity, meters per second, 340 meters per second. Okay. Now similarities between the stationary and a progressive wave. A stationary wave, the first thing is, in a stationary wave you have particles at nodes and particles at antinodes. The particles at node is always at rest, whereas in traveling wave there is no particle which is anytime at rest, which is always at rest. Anytime any particle can be at rest, but there is no particle which is always at rest in a traveling wave. But in standing wave you have such particles. Okay, in standing waves you have antinodes who can have maximum possible displacement all the time, but in traveling wave you have no particle which will always have maximum possible displacement. In a traveling wave, energy is transmitted from one region to another, but in standing wave, energy is always confined in one area. Say, I'm going to just do one thing. I'm going to just give you in written form. So let's check this. Okay, so just going through it, say you can pause and read through it, right? Sometimes they are part of the multiple choice questions, stationary, the difference and similarities. Sometimes it's 1 mark or 2 mark question. So it's a simple question. There's no point losing marks in this one. Now let's do some question. Which statement is true for both stationary and progressive? Is energy transferred? So, okay, yes. If you have been doing my videos, you know that. I don't know why my PowerPoints end up taking this dot. Okay, so again, pause and find out the answer. The first is, then the second one, particles move perpendicular. Then this in stationary waves. Pause, the answer is particle between two nodes are always in phase. A student investigates stationary waves in a resonance tube. This tube is closed at one end. A tuning fork of frequency 340 Hz produces the first resonance when air column is length 25 centimeter. Explain the formation of stationary waves in the tube. Okay, pause and do it. If you have done it, then check your answer. Okay, so that's it for today. So stationary waves, kind of this. So when a string is vibrating in a stationary wave, as you can see, the first one is, so this one is first harmonic, then second, third, and fourth, and so on. Harmonics are produced both in strings and pipes. It could be an open end pipe or a closed end pipe. Stationary waves, nodes and antinodes are formed. So revise, rewind, revise again. Well done for learning and watching. Thank you so much.